Okay, here's another example of a power series. This one is not centered at 0. It has that x minus 3 to the n term in it. And so this is actually centered at x equals 3. I mean, we can see this if let's just write out some terms of the series like we did before. So if we plug in 1, we get x minus 3 to the first power over 1 times 5. X minus 3 squared over 4 times 5 squared. It doesn't really matter what number that is. It's 100, but it doesn't matter. X minus 3 cubed is the next term over 3 squared times 5 cubed, and so on, right? And it's that thing I say centered at x equals 3 because if we plug in x equals 3, all the terms of this go away and it just equals 0. And so it obviously converges for that value for x equals 3, but not for any other value of x. There, at least it's not obvious what goes on for any other value of x. And so we want to do this analysis. We could try some points. We could try plug in x equals 4, x equals 5, and see what happens. But I would say that we might as well just go to the general, now that we've seen in the previous example, this the ratio test idea. So let's apply the ratio test. Remember, the nth term is right here. This is a sub n. Then a sub n plus 1 is, we just replace n by n plus 1 everywhere. So n plus 1 squared times 5 to the n plus 1. And so the ratio test says to compute the limit, right? So the limit of the ratio of the terms. So let's just dive right into that. So we want the absolute value of a sub n plus 1 over a sub n. Remember, the whole point is going to be if this limit's less than 1, the series converges. If this limit's greater than 1, the series diverges. And if the limit equals 1, we don't know. It could be either way. But now we want to start plugging these in. So we have the nth plus first term on top. So I'm just going to copy that right here over n plus 1 squared times 5 to the n plus 1. And then the nth term on the bottom, which really means if we divide by a fraction, we multiply by the reciprocal. So n squared times 5 to the n on top, x minus 3 to the n on the bottom. And we have that. And again, as with these, we see nice cancellation, right? There's one more x minus 3 on top than on the bottom. There's one more 5 on bottom than on the top. And we still have n squared over n plus 1 squared. And so this simplifies quite a bit to the limit as n goes to infinity of the absolute value of x minus 3 times n squared over n plus 1 squared times 5. And the limit only cares about n, so anything that doesn't have an n, well, actually, let me do this in 2 steps first. So again, there's the absolute value we have to deal with, but n squared, n plus 1 squared, 5 squared, these are all these terms are positive already, so the absolute value doesn't affect them. So we can write that as the absolute value of x minus 3 over 5 times n squared over n plus 1 squared. And now the step where I said the limit only cares about n, so we can actually pull out things that don't have n's in them. So we get this comes out, the absolute value of x minus 3 all over 5 comes out in front. We can also write the n squared over n plus 1 squared as n over n plus 1 quantity squared. And again, this is something that a limit that we've seen enough times to know that this goes to 1, right? It's just basically the numerator and denominator getting closer and closer as n gets large. And so you're getting a number close to 1 and you're squaring it still close to 1. Okay, so the ratio test spits out this. This is our L. Okay, just the absolute value of x minus 3 over 5. And so what we do is we set L less than 1, right, to find the radius of convergence. Actually, this is what's going to help us find the radius of convergence. set L less than 1. So that means absolute value of x minus 3 all over 5 is less than 1, which means the absolute value of x minus 3 is less than 5. And this is an interesting statement. I mean, if you haven't looked at these for a while, there's a couple different ways to think about this and identify the values of x. You can always plug in a few values of x to see, like, if I plug in x equals 7, does that work? You know? Well, if I plug in 7 for x, I get 7 minus 3, which is 4, which is less than 5, so yes. But if I plug in negative 50 for x, that becomes the absolute value of negative 53, which is bigger than 5, so no. So you could do this sort of analysis where you look at specific values of x. Or you can think about, there's a couple different ways to think about this, what absolute value means. So I like to give, there's two different approaches to this. You can do an algebraic approach, you can do sort of a geometric approach. So the algebraic approach is just to think that it turns out that absolute value of x minus 3 less than 5 means that x minus 3 is between 5 and negative 5. Right, because it's basically it's a positive or negative number. X minus 3 is a positive or negative number that is smaller than 5 in size. And so that means x minus 3 has to be somewhere between minus 5 and 5. And then you could add 3 through this and you get minus 2 is less than x is less than 8, right? If I just sort of add 3 everywhere to sort of all three sides of the inequality, however you want to say that. So that's an algebraic way to do this. You could also do it geometrically where you say the distance, the x minus 3 means the distance from x to 3. The absolute value of x minus 3 means, by definition, the distance from x to 3. Right, just to go over here somewhere, like, for example, the absolute value of 7 minus negative 3. That's the distance from x7 to negative 3 on the number line, right? Negative 3 is here, 7's over here, and the distance is 10. And it doesn't matter, I could do minus 3 minus 7, right? Either way, that's the distance. So I like this idea of this is the distance. And that distance is less than 5. So we could translate this into a sentence. The sentence is the distance from x to 3 is less than 5. Or you could say x is within 5 units of 3. And so you could draw a number line and say, oh, okay, well, we're within 5 units of the number 3. So 3 maybe is here. And if I go 5 in this direction, I get to 8. And if I go 5 in this direction, I get to minus 2. So plus 5, 5 in that direction, 5 in that direction. And this becomes minus 2 is less than, becomes the exact same thing as what's right there, right? So that's kind of the way we can see it. It's kind of nice to see it either way. But I like the geometric way. You can see this from the algebra too, but the geometric way sort of really reveals that R is 5 here. The radius of convergence is 5, right? Because we know it's gonna, we know that the series will converge for 5 units to the left of 3 and 5 units to the right of 3, and that's the radius. So, right, and so we know the series converges. Series converges for x minus, for the absolute value of x minus 3 is less than 5. It diverges when the absolute value of 3 is greater than 5. Absolute value of x minus 3 is greater than 5. And we get no info, because that's again, I'm just looking at the value of L, right? I'm looking at, this is our L. And so this expression will be greater, this expression right here will be greater than 5 when the numerator is bigger than, it will be greater than 1 when the numerator is bigger than the denominator. So that's where I'm getting the x minus 3 greater than 5. And we get no info if the absolute value of x minus 3 equals 5. Those are the numbers that are exactly 5 units away from 3, which are, you know, x equals minus 2 and x equals 8. And so in this picture up here, we really can see maybe that the green, that the it converges from -2 to 8, and it diverges outside, and that we have these question marks at -2 and at 8. So we got to check those. But we do know the radius is 5 and pretty quickly. And then to get the precise interval, we need to check the endpoints, right? So to get the interval of convergence, not looking at. We need to check the endpoints x equals -2 and x equals 8. Okay, so let's try x equals 8 first. Our series was this guy, just recopying it. If we plug in x equals 8, right, we're going to plug in x equals 8 right here. Then that just becomes 8 minus 3, which is 5. So we get the sum n equals 1 to infinity of 5 to the n over n squared times 5 to the n. And very similar to the other example we did, the 5 to the n's cancel. And now we actually get the p series 1 over n squared. And this is p series with p equals 2. And so we've showed a bunch of times that this converges. Right? Okay, so that endpoint converges. What about the left endpoint when x is -2? Well, if I plug in x equals -2 up here, then we get -2 minus 3. So we'll get a -5. That summation sign does not look very good. So we'll get -5 to the n over n squared times 5 to the n. And we sort of said you could write this out term by term until you see the pattern, but we can factor the numerator as -1 to the n over 5 to the n, -1 to the n times 5 to the n, sorry. And we have the 5 to the n in the bottom still. So now these cancel, and we're left with just -1 to the n over n squared. And we actually already know that the absolute version of this converges, right? This is alternating. But it converges absolutely because the absolute version is right there. So we could use the alternating series test on this, but we could also we know if a series converges absolutely, then it converges. So alternating, so it's absolutely convergent. So it's convergent. Okay, so that converges too. So in fact, in this example, both endpoints converge. So if we draw the interval again, centered at 3, 5 units to the right gives us 8, 5 units less gives us -2. Then we actually know, let me draw the bubbles here. Then we actually know that this converges at -2, so I can fill that in from -2 to 8 and fill that in. So it converges at both endpoints and it diverges outside of that. Right? And in math, we could say, so that's smaller. So the series converges for the values of x that are less than or equal to 8 and greater than or equal to -2. And this is the interval of convergence. Okay. Stop there.